This is cancer population dynamics or cell population dynamics in cancer. And before we begin, don't forget that the workshop is being live streamed, recorded, and it will be distributed. So no crazy things in the camera, okay? Okay, let's start. So this is the simulation we want to build. It's a simulation where you can track cell strengths. So the cancer divides and it may vary its phenotype. So we want to keep track of this phenotype and see the impact of some cell behaviors in the simulation output. And also track the number of cells. So we can, for example, analyze cell population stuff, okay? But before we build a model, we will go through a step-by-step philosophical model building here. So something along the lines of what James was teaching today. So some questions we have to ask before building a model. I put some examples here. They are not in order. For example, what is the objective of the research? And I put research instead of model because the model comes after you decide what you're going to research, right? What questions you want to answer? So what questions could be, for example, how can I treat cancer better? How do I distinguish two different types of cancer? Or how a model helps you in achieving this objective? This is a very important question because sometimes you don't need a model. Sometimes you need a model. And how your model, your specific model, let's say a Computational 3D model, can help you achieving the objective of your research. This is a very important step. What are the experimental observations telling about the system you're going to model? This is important as well because you need some basic hypotheses about the system you are modeling to set rules, set interactions. Otherwise, you are just walking in the night. These questions are not in order. So, for example, you can always start with an objective. Then you go see what the experiments are talking about, or the other way around. You see the experiments, you see the results, and then you start, for example, setting objectives for your research. Then what are the hypotheses you want to test? And what are the main behaviors you want to represent in your model? So, for example, in the case of cancer, growth and division are important behaviors. Migration, is migration an important behavior? Depends on which type of experiment you want to model, to reproduce. So if you are just modeling a tumor, solid tumor that grows and fights back the immune system, you may not need migration. If you are modeling metastasis as well, then you need migration, so on and so forth. Okay. So these questions are not in order. So I will present an example. So this is a simulation. So let's say I am researching cancer, and then I see some observations, reading the papers. Some of these observations are cancer is made up of stem cells and somatic cells. The somatic cells have limited division capacity, which means, for example, if they have 6 generations to divide, after the 6 generations, the cell will die and stop generating child cells. Stem cells, on the other hand, are unlimited in terms of division capacity, so they can divide forever. Stem cells can divide both symmetrically and asymmetrically, which means symmetric, basically one stem cell will generate 2 stem cells, and asymmetrically, one stem cell can generate a stem cell and a somatic cell. Another very important observation is that many cancer types have a very small proportion of stem to somatic cells. This is a very important discussion today. People agree on this result. And in this table here, you can see the ratio of stem cells to somatic cells. For example, in breast, one somatic cell for every 1,000. I'm sorry, one stem cell for every 1,000 somatic cells. So the proportion is very low, all right? Now let's think of our objective. What do we want to achieve with this research? So for example, determine the impact of phenotype distribution in cancer growth rate in breast cancer cells, for example. So let's say my friend Hayden in the wet lab is working with breast cancer, and he can somehow measure phenotype differences between cells, and he can plot a histogram of these differences. And we want to study, for example, how the width of this distribution impacts the growth rate, and then build a simulation to study this behavior, right? Some examples of questions we can make about this system, these observations. Do treatments that kill stem cells are more effective than treatments that kill somatic cells? Yes or no? So for example, if stem cells are the basic, the fundamentals of the cancer growth, maybe targeting them is better than targeting somatic cells. So is there a proportionality that achieves greater results or not? Do mutations in cells help or harm cancer growth? So let's say our cells mutate with a particular probability. Does this help the cancer to grow more, or does it harm the cancer? And a third question, how somatic cells can help stem cell survivability? Because this particular example of cancer system I'm talking about, the more stem cells you have, the better it is for the tumor, because you generate a greater amount of cells, because somatic cells have a limited division. And somatic cells, the larger, not the larger, but the bigger the quantity of the somatic cells, the worse in this case. But let's say the somatic cells help protecting the stem cell. Well, in this case, if they help protecting the cell, maybe there is a ratio of stem to somatic in the cancer that increases, maximize the survivability of the cancer, right? So these are all important questions we can ask about this system. How a computational model can help us answer those questions. So, for example, we can test different kinds of treatment and average over a large set of samples, which in the experimental side of things would be very expensive. I don't even know how you could do this over and over again and average, but no, this one is not difficult to think of. But the second point, for example, regulate phenotype variability and see the impact of it in cancer. This would be trickier to do because you have to, for example, separate cells with identical phenotype and grow a tumor from them, and then do the other way around, mixing different types of cells. So it's very expensive, very hard to do in an experiment. So simulation allows you to almost for free test many hypotheses, as long as you build your simulation according to the experimental observations with solid hypotheses. What behaviors we want to include in our simulation? So the most basic ones, the fundamentals for our simulation are growth, division, a limited number of divisions for somatic cells, which is also called senescence, and stem to somatic differentiation. So this I called asymmetric stem division, and obviously cell death, right? But there could also be other behaviors. For example, contact inhibited growth that Gilberto taught today, epithelial to mesenchymal transition, to begin metastasis, for example, migration to model metastasis, nutrient consumption, and these behaviors would add extra layers of complexity to the simulation. And we only add each of these behaviors if we want to answer a specific question that relates these kinds of behaviors. For example, how big can the cancer be if the surrounding medium can provide only a fixed amount of oxygen? So in this case, we add nutrient consumption, we add a diffusion behavior for this oxygen field, we make the cells absorb the oxygen, and as oxygen depletes inside the cells die, and then we see the impact of nutrient consumption in the cancer growth. And all these could be important for other research objectives, but there are others that we don't want to implement. So I put some absurd ones like teleportation, which is not actually absurd. When I was discussing this with James, he managed to creatively create a situation where you would implement teleportation for cells when you, for example, are simulating metastasis, but you want to neglect cell migration time. You can just teleport the cell and see what happens. But time travel, this one, James cannot make this one useful, so I put time travel. This is the joke of this slide. So yes, let's start with the exercise. So first things first, we want a system with stem and somatic cells, but our cells needs to die when they reach maximum division capacity, the somatic cells. So we also need necrotic cells, which are the cells, the dead cells that must disappear from the simulation, okay? So let's start. I will open my to edit. And by the way, all the simulations that I'm going to build, they are in the drive. So you can acquire them for free without building anything if you are lazy. But if you want to learn something, please follow my lead. So first things first, let me close this one. I think I will have to close and open again to edit. Yeah, this is already the spoiler. I'm sorry. I shouldn't be showing the spoiler. Okay, here's my to edit. Start a new simulation. So CC3D project, new simulation, Pedro is nice. Python plus XML, basic, and nothing to change here. Next. In the cell type specification, please set the names in the slides. So stem, add, somatic, add, necrotic, add. I know, guys, this is a very difficult step, so I'm giving you time to set the names of the cell types, okay? So Cool time travel works similarly with something remaining after treatment and not getting detected, but it becomes important in the future. So you don't need that. That would be the wrong usage of the term time travel. I think this kind of behavior would be um, I don't know, lingering something, I would call it. So let's say a treatment, you put like a medicine, a drug, and it decays, but it lingers. And let's say if you use another drug, both drugs will interact, for example. But this is not time travel, right? Don't need time travel to do this. But keep thinking. That's the spirit. Okay, I'll move on now. What's the next step here? Okay, so chemical fields, ignore cell properties and behaviors. Contact, volume, local flux, growth, and mitosis. And we are time traveling at the rate of the light speed, actually, which is very interesting. I will relaunch the poll to make sure you guys are following the steps. Okay, so why contact? Well, because we need cells to maintain shape, etc. Volume, because we need cells with size. Growth, because we want cells to grow, and mitosis, because we want cells to divide. So nothing too special about this part here. Okay, next, finish. There you have your simulation. And now what we want to do is start with 4 stem cells in the middle of the lattice. So go to your XML, go to the bottom of your XML. There you will see a steppable uniform initializer. So you delete the somatic and the necrotic, leave only stem cells. And for example, from 120 to 130, this means a 10 by 10 square in the middle of the lattice. So if we also set here the width to 5, you have a 10 by 10 square, which means 4 5 by 5 squares. So this way we are initializing 4 stem cells. If you intend to learn Computational Model materials instead of biological systems, keep in mind that this specific model carries information about instructions of how to plot things, how to track things in the simulation. So stick with us. Okay, go to your staples and In the initialization, you will see this target volume, lambda volume. We increase the lambda volume because this very low lambda volume of 2 has a high probability of killing cells stochastically, only through thermal fluctuations. So increase the lambda volume to 10. And now let's run the simulation. Let's see what's happening. No module named Pedro is nice. Steppables. Oh, there is a problem in my .py. Let me see here. Steppable. This is very strange. I'll try setting this up real quick. Okay, it runs. Now I will redo the steps I did before. I'm sorry for that. I never encountered that bug before. 5 and only stem cells. Yeah. Okay, it runs now. I mean, stochastic bugs as well, you know. Sometimes they randomly appear. You don't know how. Okay, but this is very strange because we started with only stem cells, and now we have, if we see down here, we have the gray ones are the somatic cells in my case. I'm sorry, this will be switched for me because I messed up before. But the stem cells are the red ones, the somatic are the gray ones, but I only started with stem cells. Well, there is a problem with the cell division setup, which is if you go to your steppables in the mitosis, you will see that in line approximately 66, you are setting your child cell to a different type than your parent cell. Okay, so we need to get rid of these 2 lines, these 4 lines actually. So you can delete, you can comment. All right, now I run. Stop, run. Now we have only stem cells, so my red cells are stem, and they are growing. Okay, beautiful. Are you done with the exercises? Okay, that's very good. Next step. Let's see what we have next. Now let's make stem cells divide asymmetrically. So with some probability, the stem cells will divide and they will generate a somatic cell rather than two stem cells. So if you don't understand this division dynamics, please ask in the chat. That's what I'm going to do now. So in your steppables, you will define a global variable P equals 0.5, the global variable. This will be our probability to divide asymmetrically, okay? And take that opportunity and import random as RD because we are using probabilities. In Python, random is a good library for random things. So import random as RD. And then if we go down to our update attributes method in the mitosis steppables, so it is around line 57, we will see that in the original setup, our cells are being cloned. The parent cell has its attributes cloned to the child cell. So instead of this, we will set a probability that the child cell become a somatic cell. So pay attention here. If the parent cell is a stem cell, so somatic cells won't go through this testing. So if the parent cell is a stem cell, with 50% probability, it will generate a somatic cell. Okay, so let's do this. If I will keep the slide open because it helps me as well. So if the parent cell, if the parent cell dot type, so we are acquiring the type of the cell now. If the type is stem, okay, so equal, equal, double equal, you are testing if the two are equal. Okay, so if the two are equal, then now we test, we apply our probability. So 50% probability, how do we test a 50% probability? Pick a number, a random number between 0 and 1, a float, and test if it is less than 0.5, which is our...
Pedro, slow down.
Yeah.
You haven't told people what type names are. So the idea of self.stem has not been introduced yet in the lectures.
Oh, okay. Sorry. Okay.
There is the idea of iterating over lists, so you better go over that too. Slowly.
Okay. So what's happening in the mitosis steppables? Here in the line 45, so pay attention here to my code. In line 45, we are looping over all cells in the simulation. So for cell in cell list has all cells in the simulation. And for cell in cell list, you are looping over all these cells. Then we test if cell volume is bigger than 50. Why 50? Well, because our cells have initial volume 25. So volume 50 is the double of that. So if they have a volume larger than 50, we append the cell to a list of cells that we want to divide. So they reach the double of their volume, and then we want to divide them, okay? Now we are making another loop for cell, but now not in all simulation cells, but only in the cells that belongs to the cell to divide list. So for all cells in the cells to divide the list, we apply this method, divide cell in random orientation. So we apply this method to the cell, which divides the cell. This method divides the cell. Questions? I will repeat myself one more time. Cell list is the list of all cells in the simulation. Each object in this list is a cell object. So you can access their volume, you can access their pressure, you can access their lambda volume, you can access their surface, you can access everything. And for cell in cell list, you are looping over all cells, all cell objects in the list of cells. Okay? Then here is the arbitrary stuff for this particular simulation. You test if their volume is bigger than 50. So notice here, cell is our cell object. So dot volume, here we are acquiring a property of the cell, which is the volume of the cell. And we're testing if this value is bigger than 50. Then we are appending it to a list. So we are taking that list and we are inserting a cell in this list. So the list grows in size and now carries this new cell. Then we will make another loop now over cells to divide. So we have the list of all cells we want to divide, and we loop among all cells in this list and apply the divide cell in random orientation method on each cell of the list. So this method here is effectively dividing the cells. Is it clear so far? Yes or no? Okay, I'll go on. If you're not following, you must type no. Otherwise, you will fall behind, okay? You must type no. So in the update attributes, what this does is, for each division, the update attribute method will clone the parent cell attributes to the child cell attributes. Okay. So if your parent cell has a given lambda volume, a given surface target volume, a given lambda surface, a given dictionary, I don't know what, everything will pass to the child cell, will be cloned. The cells will be identical except for their positions. Okay. And we are taking advantage of this function. So we are extending this function now in the purpose of this code here to make the child cell different from its parent cell, because sometimes the stem cell will generate a somatic cell with a 50% probability. So we are, after a cell divides, when we do clone parent to child, does it clone attributes to both the two? Yes. No, it's not two children. You have one cell, and when it divides, one cell remains the parent cell, and the other is the child cell. Okay, so it's cloning the attributes of the parent, which still exists, to the child cell. Good question. Good question. Thank you. Okay. So now we are extending this function. Instead of cloning all attributes now we want to make the child cell a somatic cell. So with 50% probability, the child cell, which we can access typing child underscore cell, okay? And now we access the type of the cell, which is stem, Okay, the type of the child cell is stem because we cloned everything. We will set it to, what is it? Somatic. So I will repeat this one more time. The parent cell is the original cell. Here we are accessing its type. Dot type, you are accessing the type of the cell. So if it's stem, if the type is stem, with 50% probability, we want to update the type of the child cell to somatic. Is it clear? I will wait for a no in 10 seconds. If I don't get a no, I will proceed. Did we define P somewhere? Perfect. Yes, we defined P as a global variable in the beginning of the simulation, as well as importing the random package. Yes. Thank you. Okay, I'm going to get back to the slides. So these are the changes I'm making. With 50% probability, a child stem cell will become a somatic cell. It's child underscore cell. Okay, I will save and run. Let's see. Where is it? Here. So now, yes, now we are getting some somatic cells. And there is a very particular outcome here, which is we have much more somatic cells than stem cells. But stem cells keep dividing, okay? So I will launch the poll because I am afraid some people are not following. I will launch the poll. Let's see at which stage you are. And if you this is I'm just covering what Gilberto taught again, okay? So just to be sure you guys are following. Okay, I will proceed. Next step. Let's implement now our division capacity, because in our simulations, cells are not dying for because of their limited division capacity, because we didn't implement this this feature, right? So let's set a division capacity for the cells, and it must be individual for the cells. So doesn't make sense to set a global division capacity. In this case, all cells will die. It wouldn't make sense. So it is a property particular to the cell. So each cell has its own generation, has its own division capacity, right? And as it divides, it loses its division capacity, okay? So let's first define a global variable. Oh, so we are defining a global variable, yes, but now we need to set it individually to each cell. So in the constraint initializer, let's take advantage that we are already looping over the cells in the constraint initializer. So we have here for cell and self-cell list. So for all cells in our simulation, we are taking the object cell and setting a target volume and the lambda volume. Let's define now a extra parameter for cells in the cell dictionary called DC, division capacity. And it starts at DC, which is 6 in our example. You could set to 1 because it makes it's more obvious the impact on the simulation. But yes, this is our change. So set another cell property in the using the dictionary, the cell dictionary. Why is that the probability half? But there is a lot more somatic cells than stem cells in the simulation. Because stem cells, no, it is right. So each somatic cell always generates 2 somatic cells. One stem cell sometimes generates another somatic cell. So you expect that the somatic cell number is much higher. Got it, Vincent? Got it? Nice. So did you do it? Let's see, because I'm unable to follow. So someone, 3 people are unable to follow. So if you can tell us what the problem is, I will thank you. Okay, I will repeat myself once again, Melanie, while people are copying the code. So basically what happens is each stem cell can generate both stem cells and somatic cells, but every somatic cells generates only somatic cells. So there is an uneven ratio of stem to somatic. Somatic cells will divide in a larger number because somatic cells generate only somatic cells. So we will have 2 for each. And sometimes stem cells will also generate somatic cells. Yeah. Okay, I will proceed. Next step. What is the next step? Yeah, so each time a cell divides, a somatic cell, each time a somatic cell divides, it must lose 1 division capacity, okay? So this is how we are limiting the division capacity for the cells. So in order to do this, let me delete this. Oh, I shouldn't delete this because I'll mess up the line count that you guys have. So each time a somatic cell divides, we must reduce its division capacity by 1. So let's first get the somatic cells. So if the parent cell type is somatic, reduce by 1 the division capacity. Is that clear for you guys? So if parent cell dot type, here we are acquiring the type of the cell, if it's equal to somatic. So inside this if, all cells are somatic cells inside this if, then we update the division capacity. So DC minus equal is a decrement. So you subtract 1 each time a somatic cell divides. Okay? The division capacity dictionary defined? Yes. So let's get back here. In the start function of constraint initializer, we have cell dictionary equals DC. DC is our global variable, which is 6. All right. Oh, sorry, Sharon. My fault. Thank you for letting me know. And after you reduce the division capacity of the cells, we must test if it reaches 0. Because if the division capacity of a cell reaches 0, we want the cell to die. So change the cell type to necrotic to make the target volume 0. Okay. So if DC is 0, if DC is 0, change the type of the parent cell to necrotic. And then update its target volume to 0 because we want to kill the cell. So target volume equals 0. So I hope this is somewhat better for you guys. I can even close this. Yes. No, stem cells are invincible in this particular simulation. So the more somatic cells you have, the more stem cells you have, the better in terms of the tumor growth for this particular model. Okay. So yes, well observed. But there is one extra detail. The necrotic cells are also growing in the simulation, because in our growth module here, so let me centralize and show everything. In our growth, which is in line 25, we are looping over all cells in the simulation. But we don't want this. We want to loop only over stem and somatic cells. They need to grow. The necrotic cells, we don't want them to grow. Otherwise, they will not die. Sometimes you will have a big necrotic cell in the middle of the simulation. So instead of looping through all cells in the simulation, we make a loop in the cell list by type. And we give the types. We want the stem and we want the somatic. That's all. Let me try to fit everything. Yeah, this one's a bit awkward. But for cell in cell list by type, stem and somatic, you update the volume by, I don't know, 1, could be less, I don't know. Are you guys following or not? So my colleagues from Brazil, if you are not following, you are in danger. I will get back to Brazil and go after you. Yes, tamanho? Tamanho? Yes, you can. So one way of doing this would be, for example, if you want to get a specific cell, you can come here, cell manipulation, fetch cell by ID, or get cell at a pixel. So for example, I have a cell in the corner of my simulation. Its position is x equals 1, y equals 2. So you get the cell at a pixel using this, what is it? Fetch cell, cell manipulation. Get cell at a pixel, and then you put here 1, 2, and this object cell will be your cell. And now you can, for example, target volume plus equals, all right? So yes, you can. Are you good to go? I relaunched the poll because we had a few people with problems. So I relaunched the poll. Okay, let's move on. Oh, this is the result. Let's see what we got. So sometimes we'll see the cells dying. Yeah, so the other color, this strange color that I don't know the name. I won't even yeah, there is a bug. Cell is not defined. Where is it? Line 69. Oh, yes. So this is the problem. I'm sorry for this. So here it shouldn't be cell. It should be cell parent cell. This is definitely my mistake. Yeah, so I think in the slide it's wrong as well. So let's see. Yes, it's wrong in the slide. I'm sorry. I'm so sorry for this. So in the slide it's wrong. It says cell.dict, which I did as well. I think you also commit the same mistake. So it's instead of cell, it's self.parent cell.
People need you to expand the twit it a little bit so they can see the full line, not just the cutoff part of the line. I realize the split screen is always a little bit tricky to work with.
Yeah, so my mistake was in these two lines. I had cell.dict. It should be self.parent cell. Now I'll see if it runs. The dict, so the definition is in the constraint initializer. I have cell dict equals DC. Yes, here. Yes, inside start, inside the loop. Okay, now it runs. If it didn't work, I don't know what I would do. Okay, so now we see that some purple spots, some light spots, these are the necrotic cells. So the simulation is working. I'll show the code again. Yes, it has to be for each cell, yes. So important things in this particular code. P, the probability of stem cell dividing asymmetrically, generating a somatic cell. DC, the division capacity for the cells, the initial division capacity for the cells. Then we have a loop over all cells in the simulation where we set the target volume and the lambda volume. And this should be 10. Setting the dictionary, the DC dictionary to DC. So all cells start with division capacity 6. Okay. Then in the growth steppable, we loop over cells of only stem and somatic types. So I'll show you the full line here. Only stem and somatic types. We update the target volume by 1. In the mitosis steppables, we loop over all cells, test if their volume is bigger than 50. If it is, append to the cells to divide list. Loop over the cells to divide and divide. In the update attributes, we clone everything except that for stem cells with 50% probability, we turn the child cell to somatic. If the cell is somatic already, it diminishes its division capacity by 1. And if their division capacity is 0, they die. I will proceed. In all cells, but we just don't mess with it in stem cells. That's right, Lampros. That's right. Plots. We don't have time for this, but yes, you can plot in Computational. So the simulation is uploaded. Okay. The next exercise is much more important than this one. So if you want to see how the plots are made, Gilberto taught it, and you can take my simulation in a drive, which plots the number of somatic stem cells and the...
Just walk them through the plot definition. You have it up on the screen.
Yeah.
It takes more time to say you're not going to explain it than to explain it.
All right. So you can import the setup coming here, Python, scientific plots, and you can import the setup and the step, the add data points. So I'm showing the slide.
Walk them through what's on the slide that you're displaying.
Yeah. So here in the slide, it's the setup, which I just showed you.
Explain each component of the call. Again, just title, et cetera, walk them through each piece.
Okay. In the setup, you must define it in the start function, and you define a window. You get a window object for the plot, and you define the different plots you want to have in this window. So for example, one of the plots is named stem, the other somatic, the other necrotic. You can set the style of the plot, could be dots, could be lines, the color, and the size. The size both of dots if you're using dots, or the width of the line if you're using lines. Okay, so plot win is the window object. The add plot method, you are adding another plot in the same window, okay? And you name the plots as you like. In the plot window setup, you can set the title. So for example, number of cells, the x-axis title, Monte Carlo step, and the y-axis title number. In the step function, you import the add data point. In the add data point, you must refer to the specific plot you want to add the data, and the x coordinate of the point and the y coordinate of the point. So this is how you would calculate measure the number of cells for each type. So for example, each time you divide a somatic cell, the n somatic number would grow by 1. Else, the number of stem cells would grow by 1. If your somatic cell divides, it grows by 1. If it dies, it doesn't grow by 1, and your necrotic number grows by 1. That's how you would measure the numbers, okay? But let's jump straight to the interesting model here, which is implementing phenotype variation among the cells. So this is a next layer of complexity in our simulation, where we have the stem cells dividing and the somatic cells dividing as well, but we do not have any variability between them. Sharon, good question. So I don't know, maybe Juliana. Oh, Chile knows and I don't. That's interesting. Very interesting, indeed. But in the case of the necrotic cells, you have to count because they will die. You have to cumulatively count the necrotic cells. Yes. So yes, much better than my way. Thank you, Shilin. So that's a question. I will leave it on the screen for a while, and I ask Sirena to answer it. Sirena, please. How would you implement phenotype variation among the cells of this simulation? That has obviously a meaningful impact on the simulation output. Yes, you. How would you do it? Which parameter would you change if you were modeling a phenotype variability or a genetic variability? I don't know. Which parameter do you think is most interesting? Okay, don't worry. Don't worry, I'll go ahead and explain it. So one interesting variability for the cells we can change is the division capacity. So each time a stem cell divide, it can alter its division capacity and pass it to the child cells. So for example, a potential somatic child cell could be born with a higher division capacity, and some others could be born with a lower division capacity. And how would this change impact in the simulation in the end? Okay, so if we account for both mutations, both for lower division capacity and higher division capacity, how does this impact in the simulation in the end? So yes, this is other option would be to change the probability that a stem cell divides asymmetrically. So if we increase the probability that a stem cell divides asymmetrically, we increase the number of somatic cells. In the other hand, if we lower this probability, we will increase the quantity of stem cells. So we could play with this parameter as well. Either way, when you are implementing mutation rules, you must guarantee that these mutations are unbiased. Otherwise, your output will be obvious. So for example, a unbiased mutation rule would be incrementing DC by +1 or -1 with same probability and no bounds. For example, if I reach 0 division capacity, I can still go lower. I can still go to negative numbers. So this is what I mean by no bounds. Okay, and if I reach, let's say, 10 division capacity, I can still go further to 11, 20, 50. Okay, and some examples of biased mutation rules. For example, if I set the same rule, I can increment by 1 or by -1, but I set a bound at 0. What will happen is that there is more cells will have division capacity above 0. So this bound makes my distribution asymmetric in relation to our initial division capacity. So this would be a biased mutation rule. Other biased mutation rule would be, for example, multiply the division capacity by 1.5 or 0.5. Sometimes you ask yourself, okay, so 1.5 multiplied by 1.5 or multiply by 0.5, which means dividing by 2. This is asymmetric, and if you do this over and over again, your division capacity would tend to 0, because 1.5 is 3/2 and 0.5 is a half. So the net change would be 3/4. And if you keep multiplying your number by 3/4, eventually it will go to 0. So let's implement a mutation in our DC parameter. So first of all, create a variable called DC mutation, which is the probability to mutate this number, 0.1, let's say, okay? And now, inside the stem division, we mutate this number effectively. So go to line approximately 60, 65, where we set our, let me just readjust Windows quickly here. So where we have our stem cell attribute, we update the DC attribute for the stem cell. Okay, so with DC mutation probability, which is 0.1, with 0.1 probability, we update the stem cell division capacity. Okay, so how do we do this? If, pick a number, if random less than DC mutation, so with 10% probability, pick a random number between 0 and 1, test if it's lower than mutation, the DC mutation, which is 0.1, so the probability is 10%. What do we do now? So first, pick a number between -1 and 1. So the increment could be -1, could be +1, and could be 0 as well, right? So let's pick a number to increment our DC parameter. So DC dot choice. So RD dot choice. RD is our random package, and choice is a function from the random package that allows you to choose a number of a list. So -1, 0, and 1. Okay. So this will be our increment. Our increment can be -1, can be 0, which means the cell do not mutate, and could be 1. Okay, -1 and 1, the cell is mutating. And we always mutate incrementally. You don't, for example, update the value, I don't know, between -100 and 100. This doesn't make sense. So mutations are sequential, right? They are something along the lines of a Markov chain, if you are a physicist. So we do the mutation incrementally, right? So pick a number between -1, 0, and 1, and update the DC parameter. So self, now I won't be mistaken, parent cell dot dict DC. This is we are just getting our DC parameter, and update it increment by our increment. And do the same thing for child cells. Yes, we don't need 0, Sharon. We don't need, yes. Okay, you guys convinced me. You guys, you are tough, yes. You convinced me. I will remove the 0 from the simulation. So how are you guys going? Let's end the poll and relaunch it. It was Giuliano idea. Okay, I will proceed. You guys are going well. Ah, yes, an important detail. We must pass this mutation to the child cell as well, right? So if you have your parent cell and it divides in 2 cells, the 2 cells must carry the same mutation, okay? Yes, we assume somatic cells don't have DC mutation. Yes, that's right, Sheila. That's right. Good observation. So yes, somatic cells only lose diffusion capacity until they die, and stem cells have the potential to mutate. So the stem cells are really carrying the general simulation behavior here, both mutation and invulnerability, let's say, to division capacity loss. Okay, let's go on. Yes, so we can run the simulation already. The simulation is done. So I will run the simulation here. You can watch me. It's very cool. Cool. Cool is another thing, right? It's not cool. It's cool. So yes, you can see the necrotic cells disappearing. And here we have a bunch of somatic cells. So let's try two parameters. Let's set a 0 probability to mutate and a division capacity of only 1. Okay, because I want to show you the discrepancies between the two situations. So a DC mutation of 0. Let's see what happens for a initial division capacity of 1. Let's see what happens. So a bunch of stem cells. Now we are getting somatic cells. They are dying now in even proportion, more or less. And it keeps like this until it fills the entire space. Now, let's set a DC mutation of 99%. Very high mutation rate. So what is happening now? Now we have a much larger proportion of somatic cells. So it does have a huge impact in our simulation. All right. Even though we mutate both upwards and downwards. So it has an impact on our simulation. Okay. Now let's track the mutations. I don't know how much time we still have, Hayden?
Technically, the session just ended.
Okay, so
we can. I mean, we normally go till 6:30 for Q&A. So if you can want to take 10 more minutes or so, we can. That's fine.
Okay, so I didn't put the image, but we can track the strains, right? As I put here, so we can keep track of the strains. So this, instead of doing a guided exercise, I will fill my window with to edit and I will show it to you. Okay, what do you think about that? I'll show how to do, and it is in the slides, so you can take the slides and you can even take my simulation in the drive. So I uploaded the final simulation with graphs, with strain visualization, with everything. But I will just show for you here very quickly how someone of my level would implement it. Okay, so I want to visualize the strains. So each cell will have a different division capacity. I want this to show in the player like this, like a field color, okay? So like a scalar field. So let's do it. Let's first initialize the field. So we need to set a field. So I'm already wrong here. Let's define a start function. In our mitosis, it must be self, comma, and I will import the creation of a field. So if you come here, extra fields, you can create a scalar field for cell level. Look, we can set fields at the level of a pixel or at the level of a cell. So in our case, each cell has its own DC value. So let's create a scalar field of the level of a cell. All right. So we created the field. Now let's assign it to a self variable. Let's call it field. So this self field carries this object, this scalar field object at the cell level. Let's name it strain. Okay, I have the field. Now let's assign a value to the field. So let's take advantage that here in the step function, we are looping over all cells of the simulation. So let's take advantage of this particular method here in our simulation to set the value of the field. So let's import that syntax that I don't know. Actually, I remember, but I wouldn't know tomorrow. So scalar field right here, scalar field at the cell level right, and it must be in the step function. Import it. We don't need this because we already have our field object, okay? And it's not quite our field object. Our field object is self.field, and this is just field, so we have to update it to self.field. And the value, what will be the value? The value will be the DC of each cell. So cell.dict DC, and that's it. Now, I don't need this anymore. Now when I run, I can choose to visualize the strain field. And the only awkward thing is that medium has DC 0 by default, because it just puts a number, arbitrary number, and this is 0 for medium. So as the cells change DC, the color will change, and then the medium DC color could change as well. So we can visualize it better. So let's come here, configurations. We can fix between, let's say, -10. It must be a float, I think, and 10. Okay. Let's hope it doesn't crash. Okay. So now we can run from the beginning with a better sense of this, again, visualizing strain. Yes. So now we have a better sense of these mutations happening from 0 to 10, from 0 to -10. So as colors go to blue and go to red, we can see how far away they are in terms of division capacity from its original value, okay? So this is one way you can keep track of your strains in the simulation. And you can, using these colors, you can analyze, for example, the clustering of these mutations. So we can see some blue clusters, we can see some red and yellow clusters. This is a trend, effectively. So in the microscope, you could see these trends and develop your metrics. And together with the simulation, you can analyze the system. All right. So that's it from me today. I hope you enjoy the guided exercise. So this exercise, this is a serious simulation, a serious model. It was published by Heiko, and in the slides you can find the references if you want to see more details. And well, this is a very serious example of a simulation of a biological phenomenon in CompuCell. Okay. Could you show the code again? Yes. So what specifically are you after? So probably these lines here. You can take your snapshot if you want. For the last step in def, last step in def step, last step in def step, def step, last step. Yes, thank you. Okay, never mind. And I'm sorry to say it, but tomorrow you will have Pedro for 4 lectures straight. So you will either hate me or love me, I don't know. You added a field in mitosis steppable start, then added a update field for each cell under step. That's all? Yes, that's all. Somehow I'm not seeing the heat maps. Yeah, so in your CC3D, you have to pick you in the graphics window. You're probably seeing the cell field. So you click here, the visualization option. You can choose between the cell field and the strain. So you can switch back and forth. This is the cell field, this is the strain field. No, Sharon, I'm a person full of love. I can never waste my love. Okay, so I don't know if this is true for you guys. So again, tomorrow, 4 lectures of Pedro, it will be tough. For you, not for me, for you.
Melanie asks if you can please briefly explain what you mean by strain.
Yeah, so strain is the name I picked to name the phenotypic state of a cell. So some stem cells will have different division capacities. So each division capacity for a stem cell I am calling strain.
Sort of using it the same way as like a strain of a virus.
Yes.
Same thing with, permutated properties, basically.
Yes. Yes, it is.
Please. Sorry, please fill out the module experience poll. And then we have about 20 minutes here for questions for anybody who still has anything lingering, either about this module or anything else we talked about today. Also, if you'd just like to give us any general feedback about anything, you can use that space for this as well. And you do have the ability now to unmute if you would like to just speak your question to the room instead of having to type it all out. Yes, James asks if people would like to see a review at some point tomorrow, probably, of some of the basics of CompuCell Python. We were realizing during Gilberto's lecture that there was a mild oversight on day 1, and we did not include as much of that content as we usually intend to. So we think that taking a little bit of time tomorrow to go over that would probably be helpful to give some of what we were talking about today a little bit more context. Okay, yes, we will plan to do that then. Any questions while people are filling out the poll? Karen is having Twitter issues. Don't know how to fix them. You said your line numbers came back magically.
While I was working, whoops, sorry. While I was working on the previous exercise, in the middle they magically did appear. But just now I tried to create a new project just to see what would happen, and it came up with outline numbers. So I don't know what caused them to come back, but I don't know what's going on. And also every single project that I create comes up with the little tiny text, and then I have to do the very careful scrolling to get it to the right size. And I tried nuking the SQLite files, and I also rebooted my computer. I don't know what's going on.
Yeah, we'll have to follow up with you about that then if nobody else is having the same problems.
And I wasn't having them either until sometime today. They just started.
Mhm.
Oh my gosh, I have a project I started that came up with outline numbers, and I added a line. I just hit return and the line numbers appeared. Go figure.
Pedro Vancelas says, I left my simulation running and I realized that stem cells have disappeared. Any thoughts on that?
Yeah, so I noticed that too in my simulations. So sometimes you will lose cells because their volume is too low. The cells are growing. You have those pressure waves because you have the boundaries, etc. And sometimes the pressure is too high. The cells are very compacted, and they can disappear just because there are other cells around the fluctuations, etc. Oh, I'm sorry. Did I understand the question wrong?
Um, I'm not sure. Did that answer? Oh yeah, okay. Yeah, it looks like Vincelas. All right, thanks. Did that answer your question, Vincelas?
But the problem is that you don't have a mechanism that kills stem cells here. Only fluctuations. So